Hi and hello everyone. What we will see next is a queue with the feature that it can accommodate only finite number of customers in the system at any given point of time. Okay. So, it is referred to simply as queues with truncation or finite capacity queues, or in short MMC, which what we have seen the previous model that we have seen MMC, but now we are putting a restriction on the capacity which is a capital K, right. So, this is MMCK queues. So, meaning here like at any this K is for the total of this K is for the total system, it is not just for the queue. So, that means if there are C servers, when we are saying K is the total number of customers that can be there in the system at any given point of time, that means there is a waiting space for K minus C customers, right. That is what it would mean, right. So, that is the situation. So, it is the description, everything is similar to MMC model, like it has a Poisson arrival process with rate lambda, and there are C servers and each of them have an IID exponential mu distributed service time distributions, right, and these two are independent and so on. But the difference is that now there is a limit K, limit is placed on the number allowed in the system at any point of time. So, pictorially if you look at it, right, what you would see is that there is a Poisson arrival with this rate lambda, which is what is depicted here, and there is a finite queue. So, this number in the queue as per this description is this K minus C. So, there can only be K minus C customers who can be waiting at any given point of time, and there are C servers, each of them serves at the rate mu, and after getting served, like they will depart from it. Now, the customer who are not able to enter, right, to the system, that means that the queue size is K minus C or the system size is K, they are said to be blocked. The word is used is they are said to be blocked, okay, and since they are blocked, they have to leave. There is nothing that they cannot wait into that space. So, this is a finite capacity, though we assume for analytical purpose that there can be infinite number or any number of customers who can be waiting in the system at any given point of time. Practically, if you see in any place, right, there is nothing like an infinite capacity, right. It's just that it's a very large one which can be approximated by an infinite one. So, that things do work approximately well. But if you look at more closely, many a time you need to put this restriction to that system and then analyze the system to see what is the impact of this restriction or what could be the size that you need to have, right. So, that is the idea, right. When we develop the model, you see that we are trying to introduce one new feature at a time, right. First there was single server, then multiple servers, then now like we are trying to put a restriction on the size of the queue or in the system or number in the system, right. So, that is what it is. So, that means that now once you put the restriction, then see like you want to see like how the system performs, and you see like what is the the behavior of the system, whether it is as per your expectation or otherwise. So, this is then the pictorial representation of such a queuing system that we have here, except that. So, for the finite one, we will just make it the box is there is a closed box at this end as well. Otherwise, you would have seen the previous figure that these things were open, meaning that this is infinite capacity queues are there. Okay. So, what is the new feature here is the blocked customers, that are the customers who have been turned away from the system with after having denied entry into the system due to lack of space of accommodating them in the system, right. So, such customers are blocked customers. So, again this can be modeled by that. What we mean is the number in the system, right. It can be modeled as it will be a continuous state Markov chain, and a BDP model will fit into that. Now, it is the rates, everything will be similar to MMC, except that the arrivals rates lambda n would be equal to 0 for n greater than or equal to k, because if the system is full to its capacity, meaning that there are at least k customers are there, then it cannot enter, right. So, the rate at which it can enter into the system is basically is equal to 0, right. That is what we have to make. So, this is the only change with respect to MMC. So, this then the transition rate diagram would then be of this nature, that there is this state 0, state 1, 2 up to C, C plus 1, and now there is a finite state process. So, this is a finite state BDP. Whenever you have a finite capacity, so the states will be restricted to here, because from this point onwards, like it is lambda n's are 0. So, there is nothing like it is going, and we are looking at equilibrium. Even otherwise, initially it could be anything, but ultimately once it reaches come here, then it will remain here only. So, this will be the behavior eventually, right. So, the rates, service rates are mu, 2 mu, 3 mu up to C mu up to the state C, and from C to K or C plus 1 to K, the death rates would be C mu is a constant kind of thing, right. So, this is what is the state transition rate diagram for this finite capacity Q. So, this is a finite Q, that is what is you have to remember. Now, the steady state system size probabilities can be obtained easily using our earlier method as usual. Again, Pn's will have an expression of this form for n less than C, and for n greater than C, they will have an expression of this form, as opposed to MMC. Now, like this expression will be valid only up to capital K, like in MMC case it was up to infinity, that is the only difference that you will have with respect to this Pn. Now, once Pn's are expressed in terms of P naught, the normalization condition, which is now from 0 to K of Pn is equal to 1, right, will give me what is my P naught here, right. This is the P naught here. But now, since like the normalization condition is from 0 to K, it is a finite sum, right. This is always be 1, you do not need any condition on rho here, right, because whether this series or this series, both the series are finite series. So, there will be some value. So, this whole thing is some finite value. So, 1 by P naught will be 1 by 1 over this quantity, which is a finite value. So, this will be strictly greater than 0, and hence everything will exist. So, for no matter whatever be the rho. But you need to distinguish between the case rho equal to 1, where in this C server case, so it is rho equal to 1 means it is lambda equal to C mu or lambda not equal to C mu case is what we are looking at here. As usual, R is lambda by mu, rho is R by C, the traffic intensity. Now, for rho not equal to 1, right, this summation can be simplified, right. You recall this kind of summation, say summation sum n is equal to 0 to some m of rho to the power n, right. So, we know like this will be of this form, right, 1 minus rho to the power m by 1 minus rho, wait a minute, this is m plus 1, it will get it, right. So, this is what is the case. So, that is precisely what we might use it to simplify this. So, this you can take it out, right. So, lambda by C mu, which is rho to the power n minus C is what you will get. N is from C to K, which is of this form. If you just shift the index, then you will have this quantity which will lead you to 1 minus rho to the power K minus C plus 1 by 1 minus rho, something of this form, right. Or this is what 1 R to the power C by C factorial, you will take it out to get to this sum, and then you will get this expression for rho not equal to 1. When rho equal to 1, it is just the number of terms, so which is basically k minus c plus 1 is what then you will get, right. So, precisely this is the finite geometric sum in some sense is what will give you this expression. So, this is an explicit expression, of course, this you still retain it in this form, because this cannot be further done away with this. So, this is the form of P naught for rho not equal to 1 and rho equal to 1. So, in this case rho could be anything, like whether it could be half or 2 or 1 or anything, everything will work in the case of finiteness. So, that is one of the advantage when you are looking at the finite capacity Qs, that your theory will become nice, because anyway everything is going to be a finite number of terms, that is you are going to deal with it. So, you do not need to worry about the stability condition, because finite Qs for a finite capacity or finite, in this case if you look at this BDP structure, this is irreducible finite. So, all states are positive recurrent. So, you will have the existence of these solutions. So, once I computed Pn, P naught and then Pn's are given by this. So, I have the complete solution of steady state probabilities, right. Now, in this one can show that if you let k tends to infinity and with the restriction that rho is less than 1 will yield the MMC results. You can try few of these results whenever whatever we fully developed. Of course, currently you have this steady state distribution themselves. You can see that what happens to that when you have with the restriction rho less than 1, what happens to this, whether it leads to the same expression as you had it for an MMC. Similarly, for other expressions also, like you can try the same thing by letting this. That is one exercise that you can carry out and see. Now, for the case C is equal to 1, we will get the corresponding results of MM1K. This is also a model which could be studied separately, but since this is a special case of this, we can just reduce the results of MM1K from MMCK model. Okay. So, many results are available in much simpler form for MM1K model, okay. But you can try some of them and then we will also highlight what are those results for MM1K as well, okay. But again you can try this as an exercise. Now, once we have the steady state probability distribution, system size distributions at hand, we can now look at the expected Q length, which is much like your MMC model, but you have to worry about now this finite sum, okay. So, this is what, so LQ only you will take it up first. So, which will now be n minus c times Pn for n running from c plus 1 to k rather than infinity, which was the case in the case of an MMC model, right. Now, like you plug in the value of Pn, P naught r to the power c, c factorial into this is what then you will get, right. So, this is what you have. So, this again one more row you take it out. So, what you would get is this quantity where this r by c is what is rho. So, one row you take it out, the remaining row you will get. Now, you can reduce this to this particular sum I times rho to I minus 1, which much like the simple geometric sum, right. This is the derivative with respect to rho of this quantity. If you write it in the expanded form, you will get it nicely here, right. So, this quantity is nothing but d by d rho of this, but this we already know what is this sum, we just wrote in the previous discussion that this is equal to this divided by 1 minus rho. So, derivative of this is what then you compute, and you compute that to be this quantity, which is again we are writing it in terms of P naught r and rho. Okay. Similarly, for rho is equal to 1, we can obtain LQ because using this expression. Now, P naught and Pn of course that remain the same. So, that is P naught is what then for rho is equal to 1, what will happen, like you can obtain it from here, right. So, that is what one can do, much like similar to the other case. Now, once we have this in LQ at our hand, now we have to look at L if you want, then we know LQ plus R is what is true for an MMC model, right. But here this result is not going to be true because of the fact that some of the customers who actually come to this system for service are turned away because the system is full. So the actual arrival into the system is not going to be Poisson because some of them are being turned away, right. So a fraction, what is the fraction? Pk, right. Pk, P suffix capital K is the probability that you would find in equilibrium there are k customers in the system, and that is also the fraction of time that you could see the number in the system is k, and that will also be the fraction of customers who are being turned away, right. So that is this much proportion of the arrivals, they do not join the system because there is no waiting space in the system, right. So in that case, then what one has to do, like we have to modify this. Now then you have to compute what is the, what we call the effective arrival rate. So this is the word that will be used, you know, from now onwards when anything, when there is a when you are looking at the actual input which goes into service, right. In the earlier model that was not a problem because every arrival was going to the service after waiting in the queue, but here it is not the case. So that means this quantity which we call it as effective arrival rate is actually the one that determines the arrivals that goes into the service and get serviced by the server, right. So this is, we will be using the notation lambda effective is basically lambda times 1 minus pk, because pk, lambda pk is the proportion of arrivals which are turned away, and the lambda times 1 minus pk is the proportion of arrivals that, you know, are the rate of arrivals, right, with we are multiplying by this lambda here, proportion is mainly 1 minus pk. So this is out of those lambda, then only this much proportion actually get into the service, right. So this will be again, this is the effective rate seen by the servers, right. So and because, you know, of the pasta property here, right. So this is because the arrivals see time averages, and then the time average is pk is what is the proportion that will not be entering into the system, and 1 minus pk is, so that will also be this arrival rate seen by the servers, right. And so this would be actually the effective arrival rate. So in this R, whatever we had earlier as a lambda, now we have to modify that lambda with this lambda effective, and we have to derive the results. That is what we have to do. So this L bit, the relationship between L and LQ is actually modified to be now LQ plus, instead of R which was lambda by mu, now it is lambda effective by mu, which is basically then LQ which is equal to this. Now this is R times 1 minus pk. So the LQ plus R gets modified to LQ plus R 1 minus pk is what is the change that you will make. And similarly in the Little's law also, like, you know, we have to make that change, that replace the lambda by lambda effective. So by W would be given by L by instead of lambda, lambda times 1 minus pk. Okay, so this is actually capital K here, 1 minus pk, and WQ is W minus 1 by mu, and hence this is LQ by lambda effective. Okay. So this is what is the change that you have to make when you are dealing with finite capacity, that you really looking at all this Little's law, as you know, applicable only when it can to enter into the system, then only you are looking at inside that black box. So if something is going away, then you have to exclude that, and you have to look at the rate of arrivals into that black box, and that arrival would be lambda effective. So from henceforth we will call any such quantity as an effective arrival rate, and we will call it by the notation lambda effective, EFF. Right. Now that is what is the change, and accordingly the change will happen in Little's law, and in this one and in this one and so on, right. So that is what you need to take care when you are handling the finite capacity queues, right. But in such finite capacity queues, as we already said, an important performance measure is this Pk, which is the probability of blocking, blocking probability. Simply it will be written as blocking probability, blocking probability. For example, when you are looking at trying to model the mobile networks, right, or where this if I have to describe a model, like you have base stations and you have that will handles a particular call, and then the customer or who is on a call is moving from one place to the other. So, the call gets transferred from one base station to the other base station. Then this is what is handoff calls, right, and there is new calls which is originated from that center. So, all these quality of parameters, when you are establishing a network, wants that there is a certain value is given, and the probability of blocking, the blocking probabilities for handoff calls, for new calls should be below this. So, that is the standard that you want to maintain. Then only when you actually make a call, like you will not you will be able to connect it, right, or rather you will not get a busy tone or lines are not available, these kind of messages that you will be able to avoid. So, that kind of parameter specifications. So, basically what is given, it is given in terms of blocking probabilities, right. So, this blocking probability is effectively in this particular case is essentially this, but here we are assuming that there is a queuing component also, not just that you are getting into the. So, you may not be able to connect, but you can be queued, but but really this will make sense when we see the next model. But nevertheless, this is also one of the quantity that we always look at when we analyze the model, which is called the blocking probabilities, which is give us an idea about the proportion of arrivals turned away as they could not enter the system. So, that you can increase the capacity, suppose if you want, right, to reduce that if you have to meet certain requirements. So, to study that you will need this PK, because there is a new feature that we have introduced. So, there is a new quantity that will come. So, as we introduce more and more feature, there may be certain quantities associated with that feature that will come as a performance measures, and one can analyze that in terms of say model parameters, right. So, of course, if you want to analyze this PK alone, you go back to your this one P sub capital K. So, you will get this expression corresponding to whatever P naught which you get from here. Now, this PK alone you can analyze it as a function of lambda, mu, right, and how much if you have to increase is a all these things, server or K or whatever is the case. So, these are all parameters which one can analyze. So, that one can do for every performance measures that we develop, right, but we will not do, but of course, that can also be done, and that is what performance analysis is all about. Okay. Now, as we said that when there is C is equal to 1 with a single server, so the results are for the special case of MM1K. Now, for MM1K the expressions are simpler, because now P naught itself will turn out to be a very simple expression like this, and when rho is equal to 1, it is the discrete uniform on k plus 1 points is what then you are going to get, right. So, rho not equal to 1, you will get this expression, and Pn would be then will be equal to this expression, and LQ would be this expression, and L will be LQ plus 1 minus P naught, which you can write it for any general single server system. And here what this equation would mean is that, right, this mu times 1 minus P naught would be equal to lambda times 1 minus Pk, because we know that L is equal to LQ is this, and this is also L equal to LQ plus R times 1 minus Pk, that R is essentially this. So, that is what you will from there expression that you will get to see that this is the. What does this mean is that, so this is the system's effective output rate equals its effective input rate. We said that this is the effective arrival rate, this is the effective departure rate you can call, because when the departure will happen it will be of these things, right. So, that is what you would see here in this particular situations, right. Now, what we will do next is that we will try to do the waiting time distribution, which is a bit complicated here because of the finiteness, but for which now what we have to observe one important thing is that this part that we have to look at the arrival point probabilities or the arrival time probabilities, right, which is what earlier we have considered as an AN. In earlier cases, ANs were equal to PN, so we were happily using it. Now, because of this finiteness, right, because of this blocking that is happening, so the actual input is no longer Poisson because of the truncation at size at k, right. So, hence we need to determine what is the actually the arrival point probabilities, right. So, we go along a similar argument to see that AN, which is basically an arrival is about to occur and the arrival sees n in the system, right. Again by Bayes theorem, we can write this as probability of arrival about to occur given that there is n in the system multiplied by probability that there is n in the system, right. And then its sum over all possibilities, but now n is equal to 0 to k, it is not from infinity like in the earlier case that we had it. Okay. So, this quantity again we can see that this is the probability is that lambda times delta t plus order of delta t for a small interval delta t, and limit of this tends to 0 would what will give you this probability, and Pn is this and this sum of over this. So, this means this is lambda times Pn by this sum, because why there is now k minus 1, because arrival about to occur n in the system. So, would automatically mean when there is k in the system arrival cannot occur, the probability is 0. So, the arrival can happen only if the system size is up to k minus 1. So, you will get this k minus 1 here. So, that would mean that this quantity is Pn over 1 minus Pk for n less than or equal to k minus 1. So, this ANs, because A sub capital N is 0, right. So, this quantity for n less than or equal to k minus 1 is what is this quantity. So, now you see here a situation where AN is not equal to Pn, not because the arrival process is not Poisson, but because of the truncation that happens at k for this process, that this is actually the arrival point probabilities, which is again you can express in terms of Pn, but with normalized by this 1 minus Pk is what then will give you the arrival point probabilities. So, this is the difference that you need to keep in mind, because we are using this as you have seen in the earlier model, that the arrival point probabilities we are using it in the analysis of waiting time distribution. So, that we have to keep that in mind here. The another thing which is a fact which can be used in different places, but later on also we will be using it. So, mainly what we want is that this integral quantity is equal to this sum is what we need it, but but what is this integral quantity, we can give an interpretation, that is for a Poisson arrival process with rate lambda, if you are looking at the event that by time t the number of events happen is less than or equal to m, right, and that is same as probability of the sum of m plus 1 inter-arrival times is greater than t, right. So, the m events happens by time t, and then the m plus 1 event happen after t. So, the sum of m plus 1 inter-arrival times is at least t is what then would be this event. So, this in a Poisson arrival process, n plus 1 inter-arrival times sum if I take it, it will be a gamma with parameter m plus 1 and lambda, right. These are two parameters for which this is the density, right. This is the density of this gamma. Now, we want this density to be evaluated from the point t to infinity, that is what this integral is. So, the meaning of this integral is exactly this quantity, right. Now, what we want to show is that this integral is equal to this summation, right. Again you can look at this as if something like a Poisson random variable with parameter lambda t, and you are looking at its distribution function, right. You can think about this as, you can relate this to a Poisson random variable distribution function or the CDF of a Poisson random variable with parameter lambda t and up to m is what then you want. So, this event would be then equal to this, because we know n of t, obviously it has to be this, right. N of t is Poisson random variable in a Poisson arrival process. So, obviously you will arrive at this expression, but what you want to show is this is equal to this is what you will use it. So, how do we see that this is equal to this, because for this quantity you can use it either this or this, which is basically the gamma random variable, the corresponding gamma random variable, how they are related between this Poisson distribution function, right. So, this quantity if I look at it, so that is what we consider here. What you do, you make a change of variable to make this integral from 0 d to infinity to 0 to infinity by making this particular change as x is equal to x minus t equal to u, right. Then my x is equal to u plus t and this is u and this x is again u plus t. So, that is what you get here, this expression it will have. Now, what you do is that you take this quantity alone, keep it u plus t to the power m and you write it that as a binomial expansion. Okay. This is a binomial expansion, rest of the terms are here. Now, assume that you can interchange the summation and integral and then leaving out keeping it inside only the u terms here, rest of all the terms you write it outside. So, you will get this expression where this MCI is basically m factorial divided by I factorial times m minus I factorial, that is what we will get here, this m factorial will get cancelled. So, you will get only these terms. Now, what is this integral is the well known gamma function, right. So, from which you will get this expression as the value of this integral and that will give me this. So, this is simple, the interpretation of this is exactly same, which is exactly the same as here. But what we want is this is equal to this is what we will need it. So, that is what we are going to use it in our analysis of waiting time distribution. So, now we come to waiting time CDF for the MMCK model, right, MMCK. So, the line delays can be obtained as this for t greater than 0, strictly greater than 0 is ftq 0 plus exactly the same argument, but now c to k minus 1 is what arrival can happen, right. An is what now we have to write here, right, and p probability of n minus c plus 1 service completion less than by in time less than or equal to t, arrival finds n in the system, right, that is what you get here. So, we are not writing Pn here, remember we are writing it An because we are keeping it in that form only. So, we are writing everywhere throughout all places we are writing it as Ans, right, arrival probabilities we are retaining it. Now, this one is exactly equal to this one, right, which is essentially equal to 1 minus of this quantity because of this CDF business here, right. Now, this is what we have already obtained just now as to be this particular summation, this particular summation. Now, once you plug it in here, you will arrive at this expression and you will arrive at this expression. So, this is the expression for the CDF of the waiting time of line delays or waiting time in queue in an MMCK queue in equilibrium, right. So, argument everything is the same except that now there is a finiteness because of which we cannot simplify this further. So, this will all be remained in this particular form. So, this is what, so here this is summation an and summation an times this integral, that is what will turn out to be this sum as per our previous fact, and this is further simplified by plugging it what is this quantity and then you will arrive at this expression, right. Again, if you want to see what is the probability of delay, what is the probability of no delay or any other quantities which we have did for MMC, here also you can talk about it, there is no harm or there is no problem with that, but anyway since this will be a repetition we will not do that actually, right. It will be similar the case. Now, let us look at a simple example to see like how this results can be used analyzed. It is exactly similar to what we have seen earlier, but just that we want to have some feel of how this exam will work in our case. Okay. Suppose there is a vehicle pollution testing center, you assume, or anything other than that, which has 3 inspection stalls with each with room for only 1 car. So, it can check there are in the 3 inspection place or stall that you have there, only 1 car can go and get into that. Okay. The station can accommodate a further 4 cars, so meaning in the waiting space. So, meaning totally 7 in the system is what is possible to be at any given point of time. Okay. So, the arrival pattern is Poisson with mean of 1 car every minute during the peak periods. Okay. and the service time exponential is with mean of 6 minutes. All this data is pertaining to the peak period analysis, peak period. Okay. Now, from this data, assuming that the time you are looking at in terms of minutes, okay, we have to first decide that. If you are looking at in hour, then of course all these rates would write it differently, but it's minutes, it's easier in this particular case. So, with the time measured in minutes, so we have lambda equal to 1 because there is 1 car per every minute, right. The arrival is 1 car every minute, and this is with mean service time is 6 minutes. So, mu is 1 by 6 is what then lambda and mu you will have. So, and there is 4 waiting spaces and 3 servers, and total 7 at most in the system at any given point of time. So, the system is MM37, and with this lambda and mu we compute R to be this and rho to be 2. Okay. Now, using our expression for P naught, we can compute P naught to be this quantity, which is very small, 0.0009, right, is what is you are having it, and then you can compute LQ to be this and L to be this, right, L to be this. Obviously, these are all the things that the manager of this pollution testing center wants to understand the system, like what is the thing, whether he needs to do something to improve the system. So, you need to find these quantities, right, and then W, which is basically how long someone is waits in the queue, is 12.3 minutes. So, he has 7 waiting spaces. Okay. This is we can compute straightforward, and whether it is acceptable or not acceptable, or what one has to do, these are all up to the managerial decisions, right. As we keep saying, of course, we will keep saying there is nothing that we can do about it at this level. So, basically we can compute this and the expected number of cars per hour that cannot enter into the system. So, we are looking at now per hour. So, you are multiplying by 60, and lambda times Pk is the rate of arrival that cannot enter. This is a proportion of arrival that will not be able to enter. So, this is basically, since lambda is 1 here. So, this is 60 times P7, we can compute P7 and we will see 30 cars per hour. So, this gives us an idea that okay, there need to be some serious thinking on the way this testing center is been functioning, because in an hour, on an average 60 car comes, because 1 per minute, right, but out of which you see 30 cars are being turned away. So, even with 4 waiting space, now what you do, you want to increase the inspection stalls or you want to increase the waiting space. Suppose if you increase the waiting space, you can think about it. Suppose if you increase the waiting space from 4 cars to say 6 cars or 7 cars, then what is the proportion of cars that cannot enter into the system? One, you can think, and in that case, what will be the effect of this LQ, L and everything. Now, suppose if you feel that this itself is not acceptable, that someone comes and he waits for total time that is required is this W is 12 minutes here, which means 6 minutes on an average is what is service time, right, but more than 6 minutes he waits, whether that is acceptable, you can think, right. If that is not acceptable, you can think of putting up one more inspection stall, like with that. So, which direction you want to go? So, you have to analyze. So, once you get hold of these measures, then by increasing, this is what theoretically you can do, right. This is, you do not need to actually create one stall and to see how much, what is the performance, right. So, with this understanding, you can get an idea of suppose if I increase to 4 inspection stall, what would be effect of in all these LQ, P naught, W and this quantity, how much are being turned away, the blocked cars, what is the proportion of the blocked cars, right. Or if I increase the waiting space from 7 to say 10, then what is the effect of all these things? You can analyze and decide accordingly what kind of decision that you want to make. Again, we keep saying this is how this can be utilized. Our objective is to obtain this, which is not very complex in so far whatever we have encountered, but how it is to be used is in this manner. So, most of the things, like practically if you want to utilize it, you have to look at little closely the examples, right, and see how this information can be utilized to improve the system further. Okay. So, this is a simple example for an MMCK model. So, this is another model which is again based on birth death process. So, it is a birth death queuing system, but the feature that we have added here is the finite capacity queues, and then we have seen like how one can do the analysis. We have not done the complete analysis as you are seeing, as I said, but what are the important ones that we have considered with respect to this, but other aspects like we have done for MMC or MM1 model, similar analysis can also be done for these kind of models, but we are not going to do, we will just what is the model and what is the performance measure that we can derive, and we will try to see how it can be utilized into this, to give an idea on that. So, we will restrict ourselves to this kind of behavior only, right. Okay, so with that we will end our discussion on this finite capacity queuing model. We will come back with more of BDP in the following lectures. Thank you, bye.